All right. Hello, everyone. I guess we'll get started. Welcome to today's talk. My name is Gerald. I am a sixth year studying computer science and mathematics. I actually just finished my undergrad mathematics in pure math. And hopefully this talk will be enlightening. It's all about the transcendence of E, what it means for a number to be transcendental. And we will prove once and for all that E is actually transcendental. Yep. Just before we start, you guys can hear me clearly, right? I don't need a microphone or anything? Cool. Okay. So, in today's talk, we're going to split it into three parts. The middle part is the main bulk of today's talk, but we'll briefly give an overview of what transcendental numbers are and what algebraic numbers are, and then we'll go over something called the Lindemann-Weierstrass theorem, which allows us to prove E is transcendental in an easier way as well. So we'll start with algebraic and transcendental numbers. So when we say something is algebraic, what we really mean is that a number can be generated from what we call algebraic equations. So algebraic equations are really just polynomials that we are familiar with. So these are polynomials that have integer coefficients, right? And so an algebraic number is really just a number that is a root of some polynomial with integer coefficients. So here, the key word here is that these are polynomials with integer coefficients. Obviously, if you have rational coefficients, you can always transform it into a polynomial with integer coefficients without losing any information about the roots. So even if you had rational coefficients instead, that's perfectly fine, because you can always scale all of the numbers by some integer, and you get integer coefficients. Right? So in other words, alpha is algebraic if you can find some polynomial with integer coefficients such that a0 plus a1 alpha plus plus an alpha n equals to 0, where each of these AIs, so each of these AIs come from the integers. So all of these coefficients are indeed integers. And we denote an to be non-zero, just because if it were 0, then we'll just have a polynomial of degree n minus 1 instead. And so if we wanted to be terminating, then we just set an to be 0, to be non-zero. And a number is said to be transcendental if it is not algebraic. So in other words, it is transcendental if there is no polynomial, or there is no polynomial with integer coefficients, such that whatever number you have is a root. So there are no such polynomials possible. Okay, so let's have a look at some examples of algebraic and transcendental numbers. So any rational number is algebraic because you can always find some polynomial. So if we set k equal to p over q, then this is algebraic because it is clearly a root of this polynomial qx minus p. If you substitute p over q into this equation, you get 0. Square root of 2 is also algebraic because, well, it is a root to the polynomial x squared minus 2. Each of these coefficients are clearly integers, so square root of 2 is also algebraic. I is also algebraic, right? Because, well, it is a root of the polynomial x squared plus 1. And if you have a primitive nth root of unity, so this is your nth root of unity, then zeta n indeed satisfies the equation x to the power n minus 1. So it is also what we call algebraic. Cool. So with that in mind then, one question we might want to ask then is, well, do there exist transcendental numbers? Clearly, we know that algebraic numbers exist, but do transcendental numbers even exist in the first place? And the answer is yes, they do exist because, well, algebraic numbers actually form what we call a countable set, right? So if you have the set of all algebraic numbers, you can count them one by one, or there is a way to associate a natural number with an element of the algebraic numbers. And here's a short proof of it. So the first part of the proof is, let's fix an integer n, so some integer n, and we consider the integer coefficients a0, a1, up to a capital N. And we know that this polynomial, actually has at most n many solutions, because this actually comes from the fundamental theorem of algebra, right? If you have a degree n polynomial, then you have exactly n complex roots. Some of them might be exactly complex, some of them might be real. So we say, well, if we look at only the real numbers, you know that it has at most n many solutions. So if we denote a sub n a0 to an, so if we're given n a0 up to an, and we look at the set of roots of that polynomial, then we know the cardinality of this set is at most n. In other words, it is a finite set. And if you have a finite set, you can clearly count them all, right? So you know that this set, a sub n, a0 to an, this actually forms a countable set. So this is the first part of the proof. Now we're going to say, okay, we have a way of saying, if we know capital N and we know a0, a1 up to an, then we know that the set of all roots forms a countable set. Now we're going to say, given n, we don't know a0, a1 up to an, we're going to consider the roots of all polynomials of degree n, right? So in the previous case, we were given the coefficients a0 to an. Now we're going to say, okay, well, these are going to be the set of roots, these are the set of all roots of any polynomial that has degree n. And let's have a look and see what we can say about this. The first thing you can see here is that, well, this is really just the same as the union of all roots where we fix an minus 1 to a0. So we have a way of choosing each of these components, an minus 1 up to a0. And if we can choose each of these numbers, then we know that we have exactly the set a0 to an, right? Because Bn is really just the combination of all possible roots as long as we know an minus 1 up to a0. And so the union of all of those roots form exactly the set of roots of polynomials with degree n. In other words, Bn is just a union, or is just a countable union of countable sets, right? a0, a0 up to an is a countable set. And this union, if I take an minus 1 to a0, well, this forms a countable union as well, because, well, z cross z finitely many times is a countable set. So you know that Bn here forms a countable set. And so Bn itself is countable. And the final step is the set of all algebraic numbers is just the union over all possible degrees we can choose. So we can choose n to be 1, 2, 3, or any finite number. But as long as n is some natural number, then you get exactly the set of algebraic numbers. And so the set of algebraic numbers forms a countable set. So if it forms a countable set, then transcendental numbers must exist. The reason for this is because the real numbers, the set of real numbers, is uncountable. So if we take all of the countable parts away, we get something that's uncountable. And so we have a result where the set of transcendental numbers is actually uncountable. So there is no way to go, I have the set of all transcendental numbers, there is no way to just enumerate through all of them. If you try to do that, you'll always get to a point where you miss out on at least one transcendental number, and therefore there's no way to associate natural numbers with transcendental numbers. And therefore they must exist. If they didn't exist, they would have to be countable, but they are uncountable. So there must exist transcendental numbers. Another way to kind of think about this is if I have a pool of real numbers, so I have a collection of all the real numbers, and I draw one real number out of the pool of all real numbers, the likelihood is that you've actually picked a transcendental number instead of an algebraic number. Because, well, the transcendental numbers are much larger. The set of all transcendental numbers is much larger than the set of all algebraic numbers. So this is really what this result here means. If we say that the set of transcendental numbers is uncountable, where the set of algebraic numbers is countable. Okay, so once we've sort of had a feel for what algebraic and transcendental numbers are, now we're going to get into the really interesting part of the talk, and that's proving that E is transcendental. And in this version of the proof, we're going to go with a more explorative proof. So hopefully it won't seem very out of the box, because a lot of the proofs are you have this really magical equation and then somehow it magically works. We're going to try to piece them together and hopefully get to the same conclusion that many of the other people did. Okay, so to kind of give an overview of what we're going to be doing, we're just going to look at this integral, and we're going to show the first result. We're going to show that if I multiply e to the x with this fancy looking integral, then you get this other part here, where we get e to the x times f of 0 minus f of x plus this other integral that is very reminiscent of what we started off with, except for the fact that we now have a derivative instead of the actual function itself. And then what we're going to do is we're going to choose particular values or particular functions for f of t. And then once we choose these functions, we're going to arrive at a contradiction. So the proof itself is going to start by saying, let's assume that E is algebraic. We're going to go through a series of deductions, and then we're going to get to a contradiction. And the only way to get to that contradiction is to have started off with the fact that E was algebraic. And that would mean that E is transcendental. So that is the whole idea of the proof. Okay, so let's go through part one. So what we're going to do is going to show this result first. So what we're going to do is we're just going to start off with this integral. And we're just going to integrate by parts. So whenever you have this fancy looking integral here, where you have a product of two functions, naturally, you just start by doing integration by parts. So if you just do the integration by parts itself, then you obtain this result, right? This comes from the fact that we set u to be f of t, so that u prime is f prime of t, and we set v to be e of minus t. So when you integrate it, you get minus e to the minus t. When you plug everything into the integration by parts formula, you do indeed obtain this result here. Now, notice that in this part here, we have this e to the minus x thing that we want to kind of get rid of, because we rather work with e to the x rather than e to the minus x. So what we're going to do is we're just going to multiply both sides by e to the x. And so we get this result here. Hopefully, nothing too fancy here. This is just basic integration by parts, and then we just multiply by e to the x. Okay, pretty good. So what we can see here is that if we replace f of t with f prime of t, and we subtract them, then what we're going to be left with is e to the x times f of 0 minus f of x, right? So if I just move this integral to the other side, and I factor out an e to the x, then I get this nice looking expression. And the cool thing about this expression here is that you can kind of see that this, if you take this with a bunch of, if you try to unroll it by setting f of t to be f prime of t, you can kind of see that some parts will start to cancel out, right? If I replace f of t with f prime of t and I add the two equations together, then the integral from 0 to x of e to the minus t times f of t, f prime of t, sorry, will cancel out, because when you're adding them together, this minus sign and the positive part will cancel out. And what you're going to be left with is whatever is on the left-hand side and whatever is on the right-hand side, but this time here, you're going to replace it with a second derivative. So that's what we're going to do. So what we're going to do is we're going to just replace the ith derivative with the I plus first derivative. So the ith derivative of f gets replaced with the I plus 1th derivative of f. So in the first part, we get this normal looking equation. And then when you replace f with f prime, then this part here becomes the second derivative, and all of these components here would be the first derivative. So that's what happens when we replace f with f prime. And then if you keep going, you can kind of see that we're going to get the kth derivative of f with respect to t minus the k plus 1 derivative of f with respect to t is equal to e to the x times the k derivative of 0 minus the k derivative at x. So hopefully this is not too hard to see. You can kind of confirm this yourself as well. But this is just replacing the I derivative with the I plus 1 derivative, and then seeing all of these expressions fall out. Now, the reason why this is useful is because if we add all of these equations up, so let's try adding all of these equations. If I add the first expression with the second expression, then notice that the integral on the right-hand side here would be, well, that will cancel out with this expression here. And if I continue the same reasoning, this part here will cancel out with this part here will cancel out with this part here, and all I'm going to be left with is this integral here, where we have the 0th derivative minus the k plus first derivative, right? And then on the right-hand side, we're just going to factor out e to the power of x, and we're just going to get a sum of the derivatives evaluated at 0 minus the derivatives evaluated at x. So in other words, what we're going to get is something like this, where we have, on the right-hand side, we just sum a bunch of derivatives evaluated at 0 minus a bunch of derivatives evaluated at x, and on the left-hand side, we get this nice-looking equation here. Okay, that's good. Now, that's useful. So this is something that's nice to look at. But what are some other properties that we can sort of exploit about f? Well, the first observation that we might want to make is that if I were to take high enough derivatives, I want this to eventually become 0. Because if I know that this eventually becomes 0, then this entire right-hand side, or this entire integral here, just vanishes, right? Because we're just going to get an integral from 0 to x of 0, and then that's just going to become 0. So we know that as k goes to infinity, the derivative, so the derivative evaluated at t should go to 0. What are some possible functions that we could choose that allow this to happen? Well, one way is maybe polynomials. Because if I take, say, if I have a polynomial of degree n, and I compute the n plus first derivative, that's just going to become 0, right? So naturally, a good pick for this is, say, f is going to be some polynomial. The issue is that we don't really know what that polynomial looks like, but we're just going to say, from here on out, f is just going to be some polynomial. We're going to determine what the polynomial looks like, but it's just going to be some arbitrary polynomial of some arbitrary degree. Okay. And the second thing we want to observe is that I can sort of let f of x be this nice-looking sum, the sum of the derivatives, because that allows us to re-express the right-hand side in a much more succinct way. Instead of having this sum here, what we're going to do is we're going to say e to the power of x times f evaluated at 0 minus f evaluated at x. Cool. So we will define f to be some polynomial, but we don't know the construction of this polynomial. So we don't know what it looks like, we just know that it's some polynomial. Okay. So we know, because it's some polynomial, as you increase the power for k, you know that this integral here goes to 0. And so the integral itself will vanish. And that leaves us with this nice-looking expression here now, right? Where the right-hand integral vanished, and all of my sums get replaced with capital F of 0 and capital F of x. So hopefully this is nothing too hard. And so this finishes the first part of the proof. We have this nice looking expression. We're going to use that later on now. Now we're going to actually start with the proof. This is the second part of our actual proof. So naturally, whenever you start a transcendental proof, the first thing you're going to do is to just assume that it's algebraic, because that's much easier to work with. So if we assume that E is algebraic, so E is some algebraic number, then you know that there's going to exist some polynomial, A of t, where you have integer coefficients such that if you evaluate it at e, you're going to get exactly 0. So that's what it means for e to be an algebraic number. All right, so we know that a sub 0 plus a sub 1 times e plus a sub 2 times e squared all the way up to a sub n times e to the n equals to 0. So that's all we know. What we can do is we can actually just generate a series of equalities by setting x to be k for each of the k's from 0 to n. And how do we do this? Well, remember that in the previous part, we had this expression here. So what we're going to do is we're just going to use this property here to then generate a series of equalities that we're going to use. Namely, we're going to just multiply everything by a sub k, and then we're going to see that if we add all of these up, so if we add all of these up from k equal to 0 up to n, then some things will cancel out. Okay, so the first thing that we see here is that on the right-hand side, we get a sum of a sub k times e to the k. But remember that we said that e was algebraic. And so if e was algebraic, this expression here goes to 0. And we just get this expression here on the right-hand side. So we only get one part of the right-hand side, right? So this is basically what we're saying here. So the sum from k equal to 0 up to n of a sub k e to the k equals to 0. Okay? Now, remember that we never really assumed anything about f. We said that this was some arbitrary function f, some polynomial f. We never really figured out what properties we wanted f to have. So now we're just going to examine both of these sides to figure out some properties that we might want to exploit in order to prove or in order to arrive at a contradiction. So the goal here is to basically say the left-hand side is going to be some arbitrarily small value, and on the right-hand side, it's going to be some arbitrarily large value, all of which when when n approaches infinity. And that's what we're going to be doing. So let's have a look at the left-hand side a little bit. So on the left-hand side, we can kind of see that we get a sum of a bunch of stuff. Well, by the triangle inequality, that is the same thing as saying, well, you know that it's bounded above by the sum of the magnitude of whatever is on the inside, right? That's just simply by the triangle inequality. And then we can split this up into two parts. And so it naturally then lends us nicely to, well, how big does this integral grow? That's going to be our goal here. Well, we know k is at most n. So that's what we know. K is at most n. So if that is the case, then instead of working with k, we can work with n, right? Because if we know that it works for all values less than n, then at most, it has to be n. So it's natural to work with the largest possible value for k instead of working with individual values for k. So we know that the magnitude of our integral is at most the magnitude of the integral when we swap k with n. And then we can use the fact that this integral is bounded above by the integral of the magnitude of the integrand to then kind of figure out what sort of properties we want this integrand to have. Okay. So the first thing we want to do is to try bounding e to the minus t times f of t on this closed interval 0 to n. Well, we know e to the minus t is continuous on this closed interval. So we know that it has to attain some maximum value. We don't know what it is, but let's just call it m. So m is some finite number because e to the minus t is bounded on this interval. And so if I look at the actual magnitude, the magnitude is at most m times whatever the magnitude of f of t is, right? So we ideally want f of t to be bounded above, because if it is bounded above, then we have an upper bound for our integral. So if I go back to my actual integral, then this is bounded above by m times the magnitude of f of t. And so if we can force f to have some maximum on the interval 0 to n, then we can achieve a nice bound on this overall integral. Okay, so we're just going to leave that there. We're going to now work on the right-hand side a little bit, and then once we figure out what the right-hand side is, then maybe we can come to some bound on the left-hand side. So on the right-hand side, what we want to do is we want to make this sum arbitrarily large. So remember that on the previous slides, we know that this integral was bounded above. So what we can do is we can try to make this as small as possible. And then on the right-hand side, we can try to make this as large as possible. Because if the left-hand side was arbitrarily small and the right-hand side was arbitrarily large, then we get a contradiction. And that contradiction would imply that E must have been transcendental in the first place. So that is generally the strategy that we're going to be working with. Okay, so if I consider just the sum, f of k, can I make this sum arbitrarily large? Because if I can, then naturally that implies that this sum is also arbitrarily large. Well, firstly, as we saw before, k ranges from 0 to n. So if k ranges from 0 to n, then maybe one thing we want to consider is a product of linear polynomials which have roots exactly, which have the roots exactly 0 to n. Because if we know this, then we know that if we evaluate g on any of these k's, then all of them should be 0, right? Because if I plug in g of 0, I get 0. If I plug in g of 1, I get 0, etc. So maybe this is a nice definition for us to work with. Okay, so let's just keep going and let's have a look and see if that works. So what can I say about f? If I set f, if I look at the ith derivative of f, evaluated at one of these values k, what can I say about that? Well, if I differentiate x times x minus 1 times x minus 2 up until x minus n, if I differentiate this once, then g prime of 0 is really just going to depend on one term. Why is that? Well, if I differentiate this, then the only point where g prime of 0, or the only point where my entire sum doesn't become 0, is when I've differentiated x, right? And if I've differentiated x, then I'm just going to get a bunch of numbers here. So that tells me that g prime of 0 is just going to depend on exactly one term, because every other term would have a factor of x in it. You can try to verify this yourself when you differentiate, say, x times x minus 1. If you differentiate this, then you know that one term is going to have an x by itself. And so if you evaluate it at 0, then that's just going to disappear. And so the only thing that remains is whatever is left over, right? So what you know here is that if I evaluate g, or if I evaluate the derivative of g at any of these points, 0, 1, 2, up to n, then you know that it will only depend on the one value, the one part that doesn't disappear when I plug in that value itself. Okay. Let's have a look at this then. If we differentiate x squared times x minus 1 squared up to x minus n all squared, then by the same line of reasoning, I know that the derivatives evaluated at each of these points, 0, 1 to n, should equal to 0, right? If I differentiate x cubed times x minus 1 cubed all the way up to x minus n cubed once, then again, all of these should vanish to 0. But moreover, if we differentiate this again, then all of these values disappear as well. Why is that the case? Well, same line of reasoning. If I differentiate, say, x cubed once, I'm going to be left with 3x squared. If I differentiate it again, then I'm going to be left with some factor of x, right? So in the same way, if I differentiate this multiple times, then, well, if I differentiate this twice, everything here is going to vanish because the result that I get left over would also depend on some x. So if I substitute 0 into all of the equations, all of them will have a factor of x in some capacity. And so therefore, you're going to be left with 0 in the end. Right? So for example, if I differentiate this once, I get 3x squared. If I differentiate this again, then I get something like 6x. And if I differentiate it again, then the x part vanishes. Right? So if I differentiate x cubed 3 times, then I get a non-zero value. Every other time, I get a 0 value. That's the idea. So naturally then, maybe we want to set f of x to be x to the power of q times x minus 1 to the power of q up to x minus n to the power of q. And we can freely choose q to be large enough so that, something magical does happen. So maybe that's a line of reasoning that we want to work with. Okay, let's figure out if that's plausible. Well, we know that x times x minus 1 times x minus n is continuous on the interval 0 to n. Remember that 0 to n is a closed interval. Then by the extreme value theorem or by the maximum minimum theorem, we know that that function must attain some maximum. Let's call it n. And again, we can just do exactly the same thing. So we can just say, okay, well, the bound of this entire integral is at most the integral from 0 to n of m times n to the power of q, because remember that our function itself was was each of these parts here, but taken to the power of q. So it's just going to be the integral from 0 to n of m times n to the power of q, which is equal to m times n to the power of q times n. Right? Because, well, if I evaluate this, then I get n minus 0 in the end. Okay, well, remember what we said before. We said that this part here should vanish to 0. That's what we wanted to happen. So as you take q to be arbitrarily large, this doesn't necessarily vanish to 0. So maybe we want to impose some restriction on either q or this function so that we know for sure it vanishes to 0. Well, what other function grows much faster than exponentials? And the answer is factorials. So if we divide by a factorial, then we know that whatever's going to be on the right-hand side is we're just going to divide by q factorial. And if we divide by some q factorial, then what we're going to be left with is something that goes to 0 as you make q arbitrarily large, right? Because the top part is some exponential, the bottom part is some factorial, and because factorials grow much larger than exponentials, we know that this should vanish, or this should go to 0. So maybe we want to set f to be x to the power of q times x minus 1 to the power of q up until x minus n to the power of q divided by some factorial, let's say q factorial. So this is a very natural refinement of our function. And the good thing about this is that this allows the bound to go to 0. Cool. Okay, but then what about the ith factorial of this function? Well, we know that for each k from 0 to n, if I know the derivative is at most q minus 1, then the derivative evaluated at each of these k's is just going to be 0, right? Because what we're going to be left with is still going to be some factor of, say, x minus k to the power of some q minus t, q minus t. And then so you still get this factor of x minus k. And so therefore, the ith derivative is just going to be 0 as long as I is less than q minus 1. If I were equal to q minus 1, then this also applies, right? So the q minus 1 derivative of f evaluated at k is still going to be 0 for exactly the same reason. For each of these values here, I'm going to be left with some last factor of x minus k in all of the terms in my derivative. And therefore, I'm still going to get 0. But what we also know is if I set, if I set, if I look at the q minus 1 derivative of f evaluated at 0, then and we remove one of the powers of x, then this is a factorization that we get, right? Because each of these x to the q part, that all goes down. And because I'm evaluating it at with one less power of x, so this time it's x to the power of q minus 1, each of these powers will go down and nothing else changes, right? So nothing else here changes. And so if I evaluate it at 0, the only parts that remain are exactly the term where I get, differentiate x q minus 1 many times. And so what remains is exactly all of the terms where I pull the power down, so q minus 1, q minus 2, up until 1. And then I evaluate all of these parts at 0. And if I evaluate all of these parts at 0, then I know that it's going to become minus 1 to the power of q times minus 2 to the power of q, all up to minus n to the power of q. And then I have these q minus 1 factorial and q factorial business. And all of these will cancel out, except for a q at the bottom, which is kind of nice, but also not really, because we have this fraction that we're going to be working with. But remember that this q factorial never really changed. So instead of having q factorial at the bottom, we're just going to have q minus 1 factorial at the bottom, and that will cancel out with the q minus 1 factorial that we had at the top. And so this factorization allows us to have this nicer form where we just have minus 1 to the q times minus 2 to the q up until minus n to the q. Cool. And we get exactly, so, and then we refine our f to be exactly this. And this is the, if you ever look at any proofs of the transcendence of E, they will always introduce this function here. And what we can see is by looking at some behaviors, we sort of also arrived at this conclusion as well. Hopefully in a way that's more motivating, so that it doesn't seem like it's out of the blue. Cool. So now we're going to actually go through the proof. We're going to actually figure out all of the missing parts of the proof, and we're going to arrive at the contradiction in the end. So we've now defined our function. This is a function that we're happy to work with. So let's go through and figure out all of the technical details. So what we're going to do is we're going to figure out what to do with this capital F of k, using the fact that we now know an explicit formula for little f of k. The first thing we saw was that if we evaluate the q minus 1 derivative of f evaluated at 0, we ended up with minus 1 to the q times minus 2 to the q up until minus n to the q. Again, if I evaluate the ith derivative of f with evaluated at k, that's equal to 0 as long as the derivative is less than q minus 1. Okay. Now we're going to look at all of the other values for I and k. If k is not 0, then we know that the q minus 1 derivative of f evaluated at k is equal to 0, because all of these other parts have a factor of x minus 1, x minus 2, up until x minus n, because all of the other terms have a power of q, not a power of q minus 1. So all of these other terms here will have a factor of x minus k, and so evaluating it at k gives us 0. If I is at least q and k is not 0, then these terms must have been differentiated at least q times. What that means is that it leaves us with a factor of q factorial at the top, right? Because each of those powers have to have gone down. And because we differentiated it at least q times, we know that they will leave us with some q factorial in the numerator. Every other term is also an integer. So what we have here was q factorial times some integer divided by q minus 1 factorial. And so all of these factorials cancel out except for the q at the top. And so f, the ith derivative of f evaluated at k has to be some multiple of q. And this is the insight that we're going to be working with to get to our final parts of the proof. So what we have now is that capital F of k are going to be a bunch of terms that are integer terms plus whatever we have for f, the q minus 1 derivative of f evaluated at 0. Every other term must have been divisible by q because all of them were integer multiples of q. Okay, so the first thing we know is that capital F of k is an integer. And the reason for this is because, well, all of the other terms except for q minus 1 derivative of f evaluated at 0, all of them must have been an integer in the first place. And the second thing is, this is also an integer by the explicit formula that we had for this property here, right? Because if we had this expression here, clearly this is an integer. If we now show that the sum is necessarily non-zero for large enough q, then we are done. The reason for this is because if the sum were to be non-zero, and it's also an integer, then it could not have been arbitrarily small. But remember in the previous part, we saw that the left-hand side was arbitrarily small as long as q was some large enough value. And so if if the sum of ak times f of k is non-zero, it must be an integer that is at least 1, or the magnitude of it is at least 1. And those two contradict each other. And that's the whole idea. Okay, so let's work with this sum a little bit, and let's try to figure out the missing pieces. So the first thing is, we know that the sum is composed of terms that are divisible by q, and this last remaining term here. Okay, if we can enforce this term to be non-divisible by q, then we are more or less there. We're not quite there yet, but we're more or less there. So let's figure out a way to impose this restriction by maybe giving a suitable characterization for q. Remember that what we haven't done is said, what do we know about q? So what we're going to do is we're going to figure out a characterization for q. So remember that the q minus 1 derivative of f evaluated at 0 was equal to minus 1 to the q times n factorial to the power of q. Now, if we look at the prime factorization of n factorial, which is 1 times 2, all of the prime factors, and if we know that q is prime, so if we know q is prime and greater than n, then it can't appear in the prime factorization of n factorial. Because if it did, then it must have appeared in some term preceding n, but we know that q is prime, and q is greater than n, so it can't appear in any of the integers smaller than n. So if we just say, let q be prime and greater than n, then we know that q can't appear in the prime factorization of the q minus 1 derivative of f evaluated at 0. So because we only care about what happens when q is large enough, we're just going to set q to be prime and greater than n. We don't really care about what happens for small q, but for large q, this works. Okay? So what we said here was f of k was not a multiple of q. But that doesn't imply that a sub 0 times f of k is not a multiple of q. So how do we ensure that a sub 0 times f of k is not a multiple of q? Well, what we can do is we can just set q to be greater than the magnitude of a0. And for exactly the same reason, we know that a0 cannot be a multiple. So a0 can't have a factor of q. Because if it did, then q must be strictly at most a0. But if we set q to be greater than the magnitude of a0, then we're there. So this ensures that a sub 0 times f of k is not a multiple of q. But what does that imply? Well, remember that this implies that this implies that this sum is not 0. Because if this sum were to be 0, then this term here, the q minus 1 derivative of f evaluated at 0, must be a multiple of q, right? Because every other term is a multiple of q. If this entire sum were to be 0, then this entire term here must be the negation of a multiple of q, which implies that this term, the q minus 1 derivative of f evaluated at 0, must have been a multiple of q. But this is never true because this is never a multiple of q. And so the sum is never 0, at least for large enough q. Okay, we are basically there now. Let's go through the contradiction. Let's actually explicitly write out the contradiction to make it explicitly clear. Remember that what we said here was this integral, or the bound of this integral, goes to 0 as you take q to be arbitrarily large. That's what we said in one of the previous slides. But what we just proved was that this sum is a non-zero integer. And if this is a non-zero integer and this goes to 0 as q goes to infinity, well, how is that even possible, right? Because you can take this to be something like less than 0.0001 for a sum large enough q, but we know that this sum has to be greater than, has to be at least 1, right? So this is never actually true. Because we said that these two things were equal, right? In one of the previous slides, we said that these two parts were equal, but they can't be equal in the first place because they converge to different things. And this is the contradiction. We've just proven the contradiction, and therefore our assumption that, well, E is algebraic must have been incorrect. In other words, E is indeed transcendental. And this is effectively the proof of the transcendence of E. So putting everything together, let's sort of summarize everything here. Suppose that E was algebraic. This is what we start off with. If E is algebraic, then we know there exists a polynomial with integer coefficients aj, such that a sub 0 plus a sub 1 e plus all the way up to a sub n e to the n equals to 0. We consider this function and we set p to be prime. And if we introduce this function and this series of derivatives, then we obtain this exact equality here. And what we said here was that the left-hand side, this gets arbitrarily small, while the right-hand side gets arbitrarily large. And that's your contradiction, because this can never happen. So the contradiction just comes from showing the fact that the left side converges to 0 for a large enough p, and the right-hand side is indeed a non-zero integer for large enough p, and therefore that can never happen, and you get a contradiction. Cool. So this is the proof for the transcendence of E. So hopefully, once you sort of think about how each of the pieces come together, this hopefully isn't too bad to kind of digest. The last part of the talk is to just quickly go over something called the Lindemann-Weierstrass theorem, which is a very powerful theorem for us to prove certain things are transcendental. In particular, we can show that E and pi are both transcendental. So let's have a look at the statement. So if I take a collection of algebraic numbers, say alpha 1, alpha 2, up to alpha n, and we know this set is linearly independent over Q. So there is, if I know that if I take a linear combination of alpha 1 to alpha n, then the only way for this to be 0 is if each of the coefficients were to be 0 in the first place. Then you know that the set, if we take e to the alpha 1, e to the alpha 2, up to e to the alpha n, this forms a set such that no element in the set is a root of any non-trivial polynomial with coefficients in Q. In other words, there are no possible So none of these none of these elements in the set form a root of any non-trivial polynomial with coefficients in Q. So this is a equation with coefficients in Q. But remember that we could always transform any polynomial with rational coefficients to a polynomial with integer coefficients without losing any of the roots. We just scale the polynomial by some factor, and that doesn't change the location of the roots. So we don't introduce any roots, we don't lose any roots as well. So therefore, the set e to the alpha 1 to e to the alpha n also forms a set such that no element is a root of any non-trivial polynomial with coefficients in z. And this, by definition, means that each of these elements here are indeed transcendental. So each of these elements, e to the alpha I, are transcendental. So how do we use this to show that e and pi are both transcendental? Well, let's have a look. The set 1 is indeed a linearly independent set, right? Because if I take 1 times a something coefficient that equals to 0 implies that the coefficient itself is 0. So 1 itself is a linearly independent set. We know 1 is algebraic, so e to the 1, or e, is indeed transcendental. So this is just a direct result of the theorem. What about pi? Pi is a little bit harder to see. So let's suppose that pi were to be algebraic. So if we know that pi is algebraic, then pi times I is also algebraic. But if pi times I is algebraic, then the set 1 and pi I forms a linearly independent set, both of which are algebraic numbers. But if they're both algebraic, that means the elements e to the 1 and e to the pi I are transcendental. But if we look at e to the pi I, this is a root of e to the pi I plus 1, which is a contradiction because this implies that e to the pi I is indeed algebraic. And so we're basically there. And that implies that pi I was not algebraic, but because I is algebraic, that implies that pi must be transcendental. All right, and then to conclude today's talk, we sort of talked a little bit about transcendence, but this was really looking at transcendence over the rational numbers. We can also talk about transcendental numbers over other fields as well. And it turns out that if we extend Q to be to be the real numbers, then pi and e are indeed not actually transcendental. Because if it were the case that e and pi were transcendental in the real numbers, well, this will imply that x minus e and x minus pi can't be polynomials over R. But indeed, x minus e and x minus pi are polynomials if we allow all of our coefficients to be real numbers. So it turns out that talking about transcendental numbers is really a matter of over which field we're working with. And if we're working over Q, that's probably the most interesting aspect of transcendental numbers. But you can obviously talk about transcendental numbers over R, over C, over some other intermediate field as well. And as you can kind of see, proving transcendental numbers is quite hard. This proof was quite involved. It required you to kind of be a little bit ingenious about what functions you need to pick. You need to kind of think about what properties of functions you should select. So in general, proving transcendental numbers is quite difficult. For example, we know that e and pi are both transcendental. We don't even know if the sum is transcendental. That is still an open problem. And that's something that many number theorists and many algebraists are also trying to work with. So hopefully you've learned something from today's talk. If you have any comments or any questions, I'd like to hear it as well.